Hi everyone. So let's go ahead and start section 4 of chapter 20, and this is looking at local blood flow. And what we mean by local blood flow is going in and regulating how much blood is going to the capillaries and specific tissues. So remember we talked about how there's 60,000 miles of capillaries in your body, and there's just not enough blood to fill them all at once. So local blood flow is going in and looking at how the capillaries are going to be able to go in and regulate. Okay, this tissue needs more blood right now, but this area of the body does not. So this is what we're going to be taking a look at. And remember that the whole point of the cardiovascular system is making sure we always maintain adequate perfusion, right? And this is going to be the way to help maintain adequate perfusion, but locally, when I say locally, right there in those capillaries. So local blood flow is going to depend on, of course, degree of tissue vascularity, myogenic response, local regulatory factors altering blood flow. These two we'll look at collectively as something called autoregulation. And then we're going to take a look at how total blood flow is going to affect local blood flow. So let's first start with this whole idea of degree of vascularity. Degree of vascularity, its definition is blood vessel distribution within a tissue. So one thing you might remember from 2401 is how some tissues were going to have no or little vascularity, like your tendons and your ligaments. That's why, of course, if you had a sprain or if tendons or ligaments tore, it took a long time for them to heal because of the fact that they have very little vascularity. They don't have a lot of blood vessels that are going to be distributed throughout the tendons and ligaments. But then you have others that have a high vascularity, because if you think about it, like skeletal muscle, heart, liver, brain, they're all really, constantly working. So they are in need of that constant oxygen and nutrients and picking up carbon dioxide and picking up the waste, because they are in constant, I don't want to say motion, but they are constantly working. So that's what your degree of vascularity is depending on how much blood vessel or how many blood vessels you're actually going to have in a tissue is going to really determine the local blood flow that you're going to have in that certain organ. So there are, of course, ways, if there's a tissue, one certain tissue that does not have as much, or is, I guess I should say, that is in need of more vascularity, there is a way to form new blood vessels in a tissue, and this is called angiogenesis. You might recognize genesis. We looked at this term with back in the endocrine chapter, we talked about glyconeogenesis and things like that. So it was basically kind of like the creation of something, and that's exactly what we're looking at, is this creation or formation of these new blood vessels. And what that does is it helps provide adequate perfusion through anatomical changes. This takes a long time. It's not going to just sprout overnight, these new blood vessels. It occurs over several weeks to months. So some instances where you might see angiogenesis in the body is with weight gain. If you think about how with weight gain you have extra adipose tissue, and of course adipose tissue is a tissue and it is going to need some vascularity. So that is going to be how it gets its vascularity, is through angiogenesis. And if you gain muscle, same thing that's going to happen. It's going to need vascularity, and that is going to be how it happens, through angiogenesis. And we talked about coronary artery disease. And with coronary artery disease, sometimes angiogenesis can occur, kind of forming their own little bypass in order to provide the cardiac muscle the blood that it needs to survive. However, regression can occur, and this is going to return the blood vessels to the state that it previously was. So if you do lose that muscle over time, If you do lose weight over time, then the blood vessels are going to regress too, and it will go back to that degree of vascularity that it had previously. So let's take a look at the next factor that's going to affect local blood flow. And actually, this is going to take care of two of them that was on that list. And this is autoregulation. So auto meaning self. And this is going to be a way that specific tissues, the tissue itself can go in and control or regulate how much blood is going into that tissue. So there's two mechanisms that autoregulation is going to use, and it's going to use myogenic response and chemical signals. Myogenic response, we'll talk about how it's really going in and feeling or monitoring the stretch, how much pressure is inside of the blood vessels, so they act like little baroreceptors. And then these are going to be like little chemoreceptors, so a little bit different, but they're on a more local level. We'll talk later on about these big baroreceptors and chemoreceptors. I mentioned them in the heart, but we're going to talk about them a lot more when we talk about total blood flow and not local blood flow. So with autoregulation, what happens is that so if tissues are not being perfused like they need to, if it's not getting the adequate perfusion that it needs, obviously wastes are going to accumulate, and that is going to stimulate vasodilation. And of course, with vasodilation, you open up the blood vessels in that local tissue, and then that's going to increase perfusion. And then as soon as the wastes are removed, then the vessel is going to constrict. So that's one example of how autoregulation is going to work. So we're going to take a look at a couple of different ways that autoregulation is going to work. So let's go ahead and take a look at this myogenic response. Myo is obviously going to tell you it has to do something with the muscle. And of course, with blood vessels, we know that there is going to be smooth muscle in that tunica media. So that's what it's going in and referring to as a smooth muscle in the blood vessel wall. And that's going to either vasoconstrict or vasodilate to keep local blood flow constant. So think about it. If your systemic blood pressure rises, then that is going to, of course, make the blood pressure rise in that capillary bed as well. We looked at this in the last section when we looked at capillary exchange and how with hypertension, if blood pressure rises with hypertension and the systemic blood pressure, then yeah, that is going to definitely cause a pressure change in the capillary bed. So what it does is myogenic response is going in and monitoring the stretch or the pressure. So if blood pressure rises, it's going to cause more blood to enter into the arterial, and then more blood is going to enter into the capillary bed, and that's going to stretch those blood vessels because of the pressure. And automatically, as soon as it stretches, that smooth muscle is going to want to contract because we'll talk about later on how it is going in and it's detecting this increase in pressure. We don't want a high pressure situation in our blood vessels because that can cause damage. So it will immediately contract to make sure that it's protecting that tissue, that local tissue. So the contraction is going to go in and return local flow to original level. So it can constantly monitor and make sure that it is going in and getting the adequate amount of blood that it needs and not too much. So as soon as that blood pressure decreases, then the opposite's going to happen. The blood vessel wall will not stretch. So so it is going to, it can relax. The smooth muscle of the arterial can relax, and of course it can allow more blood to flow in. So this is going to be a way to kind of constantly monitor the the blood vessel by looking at this stretch that's happening. Another way to go in and constantly monitor how much blood you need in that local tissue is constantly monitoring the chemical levels of the tissue. So what happens is there's these vasochemicals, and vasochemicals are going to go in and stimulate changes in local blood flow. So these can be, response to any type of metabolic activity that we'll take a look at, or even tissue damage as well. And when I say metabolic activity, I mean oxygen levels are changing, or carbon dioxide levels are changing because of the fact that metabolism is changing in that tissue. So we'll look at that here in a second. But you have a couple of different types of vasochemicals because you have a couple of different things that can happen in the blood vessel, right? They can go in and dilate. So you have vasodilators that are dilating arterioles. That's going to also cause the precapillary sphincters to relax. Remember, when they are going to be those garters, they're going to guard how much blood is going into those true capillaries. So with vasodilators, the precapillary sphincters relax, so that means that they are going to open the door, open the gate to allow blood into that those true capillaries. Then you also have vasoconstrictors, where the arterioles constrict, but also the precapillary sphincters are going to constrict, and so of course they're going to close off the gate and not let any tissue go into the true capillaries. They'll go through the meta-arterial and go through the thoroughfare channel if they can get through it. But if the arterioles are constricted, then they might be diverted around that entire capillary bed altogether. So let's take a look at some of these metabolic changes or tissue damage that might happen in a local tissue that could cause these kind of changes. So look at this. When tissue activity increases, that basically means that that tissue is undergoing lots of cell respiration if it's increasing, right? And remember, with cell respiration, you have to have plenty of nutrients and you have to have plenty of oxygen. But also on the other side, it's saying that it's also going in and producing lots of carbon dioxide and other waste products. So these can be signals that there's inadequate perfusion. It's saying, hey, our oxygen levels are decreasing, our nutrient levels are decreasing. This tissue is undergoing lots of cell respiration. We need blood. So vasodilation occurs. Blood is going to flow into those capillary beds, and it is going to get the oxygen and nutrients that it needs. At the same time, what's happening is carbon dioxide levels, if this is happening, carbon dioxide levels are increasing, lactic acid levels or lactate levels are increasing, hydrogen ion levels are increasing, potassium ions levels are increasing. So again, vasodilation means that more blood is going to rush in, and it's going to be able to cause more reabsorption, so we can get these into the bloodstream and get it back up to the heart, so we can get rid of it that way eventually, right? So this kind of works on a negative feedback loop, to where as perfusion increases, as we have these vasodilators that are going in and working, vasodilation occurs, perfusion increases. So as soon as oxygen levels, nutrient levels, carbon dioxide levels, all of that go back to where they need to be, vessels are going to constrict in response to that. So it's this nice constant monitoring and regulation of tissues that are in need. So let's take a look at what happens whenever there's another response, tissue damage. We looked at one of these chemicals that can be a vasodilator, and we looked at a couple of these chemicals that could be vasoconstrictors. So this is going to be what happens in response of damaged tissue, or just in general what happens with the body's defense mechanism, whether it is an injury that occurs or allergens or anything like that that can occur. So histamine, we talked about this with basophils. Remember, their granules contain histamine. And these are going to cause, I mentioned, they cause vasodilation. And of course, we'll talk a lot more about this when we get into chapter 22 about the importance of inflammation whenever tissue is damaged or whenever an allergic reaction occurs or something like that. But histamine is a vasodilator. So is something called bradykinin as well. We also have some things that we talked about were vasoconstrictors. Look, thromboxane. You might remember this from hemostasis. Hemostasis, remember, was that stoppage of bleeding, that whole process of blood clotting. In the platelet plug in the platelet plug phase, thromboxanes were released. Not only did that help with platelet aggregation, but also what it did was it helps with vasoconstriction. So it goes in and prevents blood loss through damaged vessels. So do prostaglandins as well. Lots of different prostaglandins in the body, and there is going to be a certain some certain prostaglandins that are going to act as vasoconstrictors. So this is a nice little chart that is going to go in and look at local substances. That's what we just looked at. Local substances that act as vasoconstrictors and vasodilators. Nitric oxide is another very powerful vasodilator. We'll look more at nitric oxide. I believe we look at it in the immune system, but we definitely look at it in the reproductive system. This is what we'll talk about later on when we talk about trying to regulate systemic blood pressure and systemic blood flow. We are going to, or total blood flow, which we'll talk about in a second, we are going to take a look at how hormones and neurotransmitters are going to act as vasodilators and vasoconstrictors as well. So you have some local substances that work locally, like in very certain specific tissues, and then you are going to have some things that are going to work on this whole idea of total blood flow. So total blood flow is the amount of blood transported through the entire vasculature per time. So it's looking at what's flowing through the arteries, so those elastic arteries, muscular arteries, those arterioles, and then going into the venules, and then the small and the medium and the large veins. Because obviously if you don't have enough total blood flow in your arterial system, then you're not going to have enough to get to your local tissues. So that's why maintaining sufficient local blood flow is going to ultimately depend on total blood flow. Total blood flow equals cardiac output, right? If you think about it, whatever is pumping out of the heart is going to go into the vessels and is going to flow that way. And of course, this regulation, trying to regulate total flow, is going to depend on the heart. There it is, cardiac output, right? So it's going to depend on the heart, but we're also going to take a look at how total blood flow depends on the vessels as well. So that's what brings us to our next section, and what we're going to be looking at in section 5 is this whole concept of total blood flow and how it is going to rely on blood pressure and something called resistance. And blood pressure and resistance are each going to rely on either what's going on in the blood vessels or what's going on in the heart. So that is what we look forward to in the next section. So until next time.